Okay, so thank you for staying with the last talk before the lunch. So I think I shouldn't thank the organizers to invite me to talk, but I do want to thank you to come for the conference and support this great idea to come together and try to make a new center in our university. So this is the moment that I move back. This is to the first plane that was rotated. So this is the center of the event, so don't forget. So I will tell you about Matter-Wave Solitons. So essentially, I'm an experimentalist, but what you will hear now will be mostly theoretical speculations. So I'm in a best position because I can do whatever I want, right? So I'm not the theoretician. But from the other point of view, you cannot blame me that I do experiment not good because there is no experiment here. No. But I will try to convince you that there is something interesting here in the story. So, and this is something to do with solitons. So solitons actually is a so well-known object that I don't need to introduce anything about that. But so the point is that this object is completely classical. So true, you need to introduce some nonlinearity in order to see this object. So if you go to Maxwell equations, you will not see this linear equation, do not show you the presence of the soliton. So you need to add some nonlinearity. You go to a nonlinear Schrodinger equation, you get it, even analytically. So in the case of one-dimensionality. So this is well-known results for tens of years, and there are many, many theoreticians that know how to do that now on the blackboard without any need for looking for any theory book. But I try to tell you, I'll try to tell you some different stories. So I try to say you something about, well, can we take these Matter-Wave Solitons and introduce them to the quantum world? So, and there are two key points here, so two key words in this title. So one is a Matter-Wave Soliton. So there is no need to go to matter from my point of view, to go to Matter-Wave Solitons and to do a classical analogy with the classical, or the analogy with classical solitons in other science, in other branches of science. So it's almost everywhere. And the amount of work is enormous. But what we can do as a unique approach in this story, so it's really to try to introduce them into the quantum world. And this has something to do with the quantum technology, and I hope to be able to convince you that this is indeed interesting. And but I have to say that this is a new project, and we are in the beginning of that. Okay, so this is the experimental platform, actually. So the experimental platform is based on ultra-cold atoms. So we have lithium atoms, and this is a nice picture of those atoms inside the trap. But at this point, you don't have anything special. It's already well known, some low temperatures, but it's not a soliton yet. So in order to go to soliton and to make a soliton in this story, so you have to do something else. So you have to go to different steps. So actually, you have to take these atoms and load into an optical trap, which is the conservative trap, and then you have to lower the temperature to get the quantum degeneracy, and then usually you get the quantum degeneracy in the case of repulsive interactions. So it's a stable condensate. But then the solitons is, well, at least the solitons that I'm talking about, they are bright solitons. So we need to switch, we need to make the nonlinearity negative. So we need to switch the interactions to a negative. This is what you will get at the end of the story. It's you actually tune the interaction with some collisional resonance. I'm not going to tell about this, but you also can do at the end. You take the atomic cloud and you actually release it into the one-dimensional waveguide. And once you release it into the one-dimensional waveguide, without nonlinear interactions, you just see it spread in all directions. But what you see here is, so it's quite an old results already, but it's always nice to see that it continue to keep having enormous number of citations. So I will never be able to write something comparable to that, I think. It's really difficult. But what you see here is that here you have actually a Bose-Einstein condensation in the one-dimensional waveguide. So it's a really it's not a trap in this direction. Oops, sorry, just a second. This is not a trap. So in this direction, it's just free to move. So but it's trapped in this direction. So here, this is a radially strongly trapped atomic cloud. So and then if you just wait for some time, it's propagate, and it just goes in a certain direction along this waveguide. So it goes to a certain direction because the force is applied on that. So it's actually not a completely untrappable state. It's actually an anti-trappable state. So, and you see that with time, soliton accelerates, but it's not spreads. So it stays as a single waveguide. Okay, so the point is that this soliton was essentially a classical object. So this is as a classical object as any soliton in any branch of other branches of science that you can find. So from that point of view, you can see many interesting effects, but they are on some side, this side or another side, they just comparable to other classical experiments with solitons that you can do. So the point here is that the kinetic energy is much larger than the binding energy of the soliton. So the point is that, you know, if this object is not spread, okay, but it's the life of this object is within the waveguide, so this means that there is a bound energy. So it's bound, and it has a binding energy. So, but once the kinetic energy of this object is much larger than the binding energy, then we are in a classical regime from our point of view. So, and then with classical solitons, I'm just showing you a couple of more recent experiments that were done in these objects. So, but again, all these experiments are done with classical matter-wave solitons. So I'm not saying that these experiments are not beautiful. It's hard to do that. They're very interesting and nice experiments in different groups. Here it's the group in the US, and this is the group in England. So they do hard work in order to make this experiment. But in my sense, or whatever, well, it's not only in my sense, so in many senses, this is just coming back to classical work on solitons. Here, for example, this is the collision between the two solitons. So you take two solitons, you collide in between them, and this part describes you in-phase collision. So they actually go through one another. This is one possibility to see what's going on, but another possibility is actually to consider it as a interference between two wave packets. So in this case, the interference is constructive in the middle, And here, if you have an out-of-phase collision, so this wave packet is pi phase shifted as compared to the other one, they actually repulse. They make a repulsive interaction between each other, or there is a minimal fringe here in the middle. Okay, so but this is not what I'm trying to look for in this project. So what we are trying to look in this project is really the limit where the quantum mechanical approach will be significant. So in this story, we have to go to a many-body approach and have to solve a different story. So this is not a nonlinear Schrödinger equation, but we have to solve a Lev Hamiltonian. Well, this is also a well-known model. It has well-known solutions. So these solutions are this is the eigenvectors, and so these eigenvectors has well-known eigenenergies. But then, if you consider and if you look at what is the structure of the eigenenergy of this story, there are two parts of this eigenenergy. So one is the kinetic energy of our object. So this is the central of mass coordinate. And this is the internal binding energy of the object. So this interplay between these two energy scales will bring you between, will give you the crossing point between the classical world and the quantum world. So this is how it works. So if we actually bring the kinetic energy to be much smaller than the binding energy, then we can say that the ground state energy of the system is well separated from the continuum by an energy gap. And this regime becomes an interesting regime. So the point is why it is so difficult to cross this point and to go to quantum regime is here in this number. So the kinetic energy of this object is actually proportional to the number of atoms. So it's extremely heavy, and the kinetic energy is very large. So if you want to be in this situation when the kinetic energy is much smaller than the binding energy, so you either deepen your binding energy, which is possible in one-dimensional world, but it's impossible in three-dimensional world. Either you just decrease the kinetic energy. So those of you who works in the experiment knows, with cold atoms, knows that this is not a simple task. So anyway, so it's difficult. And one of the possibility, or one of the solutions in this story is just to go to actually small mass of atoms, or to go to a light atom, and to go to a number of atoms, small. Well, it wouldn't be stupid because you are a theoretician and I'm an experimentist. And this is theory slide. Yes? Oh yeah, I'm sure. So, of course. So this is what I said in the beginning. So one of the solutions is to go to a very deep binding energy, and then everything is okay. So, but I said that going to a very deep binding energy brings you to the three-dimensional world very quickly. You know, if you are here, so in this story, so it's a one-dimensional object, right? So, and the Lev linear Hamiltonian is a one-dimensional Hamiltonian. So in theory, I live in a one-dimensional world, but in practice, in experiment, I live in three-dimensional world. And once I try to find a deeper binding energy, then I bring this object to a three-dimensional object, and three-dimensional object do not leave, it collapses. So that's the problem. Okay. Cool. So this is the quantum regime, and we try to find a way how to go to this quantum regime. If we once go to this quantum regime, then this binding energy, which separates this object from the continuum, will prevent this object from splitting away if we, for example, take this object and throw it against the barrier. So in this situation, we can see some interesting quantum superposition states. For example, this is sort of an imaginary experiment. So you take the soliton and you throw it against the barrier. So now if the kinetic energy is smaller than the binding energy, then by colliding with the barrier, the soliton cannot split into two parts. So if the opposite is correct, then it splits. And it's just like a beam split. It splits in two parts, and then you can recombine that. You will see the interference fringes, of course. But here, I'm talking about something different. So here, you either go to the left, or everything goes to the left, or either everything goes to the right. So and then you actually make a sort of noon state or a quantum superposition state whose interference is more interesting than the interference of the classical objects. Okay, so that's the dream. So let's see what we need to do, or let's see how actually we need to be good, to reach this goal. So this is a sort of a simple energy diagram or energy considerations to understand what we need to do in order to reach those elements as compared to a number of atoms in each part of the splitting wave and as compared to the kinetic energy divided by the binding energy. Well, you will see it in a moment. So small n is, so the capital N is a number of atoms, and small n is a number of atoms of one particular part of the splitted wave function. Okay? So now it can be either 0 or 1. So the ratio between them. So it's either all of them in one part or either all of them in the other part, all particles to the left or all particles to the left, to the right, or some combination. 50%, for example, if you are here, so 50% goes to the right, 50% goes to the left. So here, this is actually a forbidden region, so the red one. So this consideration of very small kinetic energy as compared to the binding energy forbids you to be here in this regime. And then when the kinetic energy goes to be about the binding energy, so when it's 1, so this is the classical region. So here, there is nothing interesting from my point of view happens. So this means that soliton actually hits the barrier and splits into two parts. One goes to the left, one goes to the right. So again, we can recombine, see the interference, but this will be the classical object, the classical interference. Well, if we go down to a certain threshold, so by simple calculation, this threshold actually hits not exactly 1, but it's a bit less than 1. So when the binding energy is a bit less, so kinetic energy is a bit less than the binding energy, this is true for a number of atoms goes to infinity. It's a bit different number if we consider less numbers. This is the threshold where those black regions are allowed, and this is forbidden. So this is because the binding energy goes very, very fast with the number of atoms. So if we consider this part very small kinetic energy, so somewhere here, this is the region where we actually have the kinetic energy smaller than even a single, so even smaller than the energy that you need to throw apart even a single particle from the story. So this is a very demanding small kinetic energy. So, but if you reach this regime, then the possible states in the collision against the barrier will be the truly known state. What is funny is that even in this regime, you also have non-trivial states, quantum mechanical states, which people call Schrödinger-Keeton states, or similar names. But here, for example, you see what this n means. So you just split it into particles, but it's either 40% goes here, 60% goes here, or either way around. So you have a superposition state. So, okay, now this was the question is what we can do with these solitons. And so the question, as I mentioned in the beginning, so in order to reach this regime, we actually need to go to a regime where the number of atoms is really small in this soliton. So we need a small soliton in any case. So then the question is, so if we need a small soliton, a small number of atoms, so can we get the deterministic number of atoms? So can we get actually the machine that will give us, if I want 10 atoms, then it will give me 10 atoms. This will be really a good thing because then I can bring some experimental protocols without count. So to get the very fast counting statistics, it works very well if you have a deterministic number of atoms in the soliton. So this protocol is also based on the idea that the number of atoms, so the binding energy of the soliton, depends very strongly on the number of atoms in it. So this is actually a very simple curve that shows you jumps in binding energy, relative binding energy, when we consider a small number of atoms, actually. So if we have 10 atoms, for example, so to go from 10 atoms to 9 atoms, the binding energy jumps. So it's discontinuous. Well, it's always discontinuous, but if you work with thousands of atoms, this discontinuity is very, very small. But if you go to a very small number of atoms, this discontinuity becomes significant. Tuk, 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 tuk. So now the question is how you climb these stairs. The idea is quite simple. So if you want to climb these stairs, you actually need to address this binding energy by some sort of the modulation. And if this modulation will pump the energy into the system, one atom will be thrown away. And at this moment, you jump out of the resonance with the modulation. Once this happens, you are out of the game, and this state becomes actually stable. So we try to do this as I promised you. We try to do that, not the experiment yet, but on computer, classical computer. And this is actually the result. So this is a solution of Schrödinger equation, direct solution of Schrödinger equation for 3 atoms and 2 atoms. Okay? So this is done actually in collaboration with people in England. So here, this is the line of a soliton with 3 atoms. So this is actually the distance between the atoms, the mean distance between the atoms within the soliton. So if nothing happens, this is what we expect to see from this distance as compared to time. So nothing happens, it's stable. So if we have 2 atom soliton, this is what happens with this state. Now if you modulate it, so the atom goes away. And this is the trajectory of a single atom that goes away. So, but this simulation is made within the trap, so it's actually this atom can come back and recombine with this soliton. So it's never escaped to the infinity. So and this is why we actually have this again, for example here, actually back to a 3-atom soliton. So this is one way to do that. So now we're actually doing that a different way because these calculations are really difficult and tough. So if you want to increase the number of atoms from 3 to 4, you are almost done for life. So, but we actually found a quite nice approach by Klaus Wagner developed a few years ago. So now we, with my students, trying to do that in a different way by direct diagonalization, which is a nice approach that gives many more possibilities for calculation of this stuff. So if this protocol works, this is what I imagine as an experimental machine. A keyboard. So I don't need all this stuff. I need like a much simpler keyboard. So 1, 2, 3, 4, 5, and so on and so forth. So now you just click a button, 7, and you get 7 atoms in your machine. Click a button, 8, and you get 8 atoms in your machine. Quite nice story. And if this works, so then we can go to creation of superposition state, detection of them. So all of this stuff where we studied in several several papers in collaboration with the England group. So now the story of experiment. So this is simple. This is the stage of the experiment. So this is under construction, tough work. So this one is especially like to have this working experiment. Anyway, this is under construction. I hope that we will be able to do that in the near future. So just 30 seconds of giving another stuff. So we still experimented, so we do something in our lab. So this is a different story, but this is not a completely different story. So it's something to do with the unitary gas of atom dimer mixtures. So, I like very extreme things. So either to work with very weak interactions, so this is the solitons, or to work with extremely strong interactions. This brings me to a theory of unitary Bose gas. So this system is extremely difficult. So solitons is very, very, very difficult to do experimentally. So this guy, this unitary Bose gas, is extremely difficult to do. Okay. So this is, you can understand if you just look at this paper that was published last year. So this is a review paper of several experimental attempts to try to see this unitary Bose gas. Extremely interesting system. Not a very simple one to understand, but it's also something that actually realizes a certain quantum simulator, because at very strong interactions, you have a truly many-body system, which is almost impossible to simulate in any imaginable classical computer. So if you do this system, you can get the quantum simulator. It worked very well for Fermi gases. So people knew now a lot about unitary Fermi gases. This work was done for recent 15 years or so. Bose gases are much more resistant for these studies. So, and we try to make our contribution to that. And I have to say that, so at this point, I will introduce my team. So, so I have a student, Olga Marte, that left actually almost one year and a half ago. And he put enormous effort in studying unitary these gases, but she left before we even understood what's going on in this story. So now we seems to be closer to understand what's going on. But you lose your students before you understand. This is not a good way to go. Okay, so I'm finished. So this is the team here, and this collaborations in the Quest member, and this is the new team, right? So hard workers. And thank you very much for your attention.